Hello, this is Eric from UNC Charlotte. We presented in a previous video how to build a basic MapReduce MPI application covering how the map and reduce phase work. Today, we will go further in MapReduce MPI. In particular, we present additional ways to create map tasks, and we will show how to use MapReduce MPI to implement cross-product, which is a central operation to many applications. The first variant of map creates tasks out of integers. Variant 2 creates map tasks out of files. The user-defined function will receive a task ID, a file name, a key value object, and a context. In variant 2, it is the responsibility of the map task to handle all the file IOs. MapReduce MPI just passes the name of the file to the map task. The other parameter of the map function specify which files are being passed to the map tasks. In the most basic usage, the first parameter indicates how many files are being passed, and the second parameter indicates the file name of these files. All the other parameters are set to 0. Let's look at some examples to see more precisely what this function does. The map task only performs the simplest processing. It prints the task ID and the file name passed to the map task. In the simplest usage of the map variant, 2 files are explicitly passed as a parameter, and that creates 2 tasks, one for each of the files. The second call only passes the name of the data directory. Still, 2 map tasks are created because the recurse parameter is set to 0, and the directory contains only 2 regular files. The third call to map is made by passing only the data directory, but this time with recurse set to 1. Running it creates 4 map tasks because it recursively lists all the files that are contained in the subdirectories of data. Finally, the fourth call is made with read file set to 1. And instead of creating a single map task for the only file passed as a parameter, the file is opened and each line of the file is treated as an individual file name that gets passed to a map task. In map variant 3 and 4, the map tasks are passed content of a file. Parameter 2 and 3 are user-defined functions, which are a substring of a file and the length of that substring. There are 2 parameters to map, which are not found in previous variant. Sepcar indicates which character should be used as a separator, usually a space or a new line. Map cuts the text in different tasks using the separator, and delta is the maximum number of characters that can appear between 2 separators. The first parameter indicates how many map tasks you want in total. MapReduce MPI will split the text to honor that number of map tasks. In particular, it means that in most cases, the map task will receive a string that contains the separator. In this code, we show 3 different values of delta. In the first case, delta is set to 30, and the files are cut in only 2 map tasks. Notice that each task contains multiple new lines. In the second case, delta is decreased to 10, and 5 map tasks are created in total. When decreasing delta further to 3, the value of delta is invalid, because it is smaller than the length of the longest line. In such a case, MapReduce MPI may return an error. In practice, the cost of overestimating delta is some loss in parallelism, and you would rather not completely overestimate delta. However, a value of delta that is too small will result in an error. Map variant 5 creates map tasks out of an existing set of key-value pairs. The map function takes an existing MapReduce object, and a map task is created for each key-value pair in that object. The user-defined function takes the key as parameter 2 and 3 in the buffer plus size format, and it also takes the value in parameter 4 and 5 also as buffer plus size. The first parameter of the user-defined function is the rank of the key-value pair in the local MapReduce object. In other words, it is a number between 0 and the number of key-value pairs stored on that MPI process. The code first uses variant 1 to create some key-value pairs. Then it uses map variant 5 to create a map task for each key-value pair created in the first phase. What the map task does is simply to copy the key-value pair in the new object. All map functions support an optional add flag parameter. By default, a call to map flushes the content of the MapReduce object it is invoked on. The add flag parameter enables appending new key-value pairs to the object, rather than flushing its previous content. Cross-product is an operation that is critical to many applications. In particular, it is a precursor to joins in relational algebra. The cross-product of two sets contains all the possible combination of an object of set 1 with an object of set 2. There is an easy way to implement cross-product if one of these sets is very small. You can broadcast it on all the MPI processes and just pass it as context to mapVariant5, which you invoke on the larger of the two sets. But in general, sets are too big for this solution to be practical. Fortunately, the operation can be expressed in MapReduce with clever utilizations of map and reduce. A first map creates as many copies of objects of set 1 as there are objects of set 2. These copies are keyed so that they are grouped together. A second map creates as many copies of each object of set 2 as there are objects of set 1. These copies are keyed so that they are scattered regularly. By reducing the two sets of key-value pairs together, we obtain a cross-product of the two sets. Let's first have a look at an implementation of that strategy on a single node. The code first generates two sets, one of 3 key-value pairs, keyed on letters, and one of 5 keyed on numbers. Then, we generate the partial cross-product for the first set with cross 0, and for the second set with cross 1. Note that the second call to map appends the key-value pairs using the add flag parameter. The size of the two sets are passed as context to enable the user-defined function to generate the appropriate key. Finally, the key-value pairs are reduced to print the cross-products. Cross 0 generates for a particular object of the first set as many copies as there are objects in the second set. The key of the generated copy is calculated so that the keys are grouped. Because the key is used for generating the cross-product, it is necessary to serialize the original key-value pair into the value of the generated pair. This is accomplished by concatenating the key and the value together and prefixing them with the size of the key and the size of the value. The cross1 function is similar, except it distributes the key of the copies rather than grouping them. The reduce user-defined function unserializes the two key-value pairs and prints them. Note that because this is the one-node implementation, we know that the pair from the first set will come first, and the pair from the second set will come second. The distributed implementation is slightly more complicated, but it follows the same structure. Each process only knows the local size of the sets, so it counts the number of objects in its local MapReduce object with a call to scan. It calculates the global size of the two sets with a call to MPI allReduce. Also, each process needs to know the number of objects in each set stored by MPI processes lower than its own rank. This is achieved by executing a distributed prefix sum computation thanks to MPI scan and adjusting its results. The map task computes keys for the objects by computing its global ID based on its local ID and the number of objects stored in processes of lower rank than the current process. Finally, there is no guarantee that the pair of the first set will come before the pair of the second set in the reduction. So we need to add an identifier in the serialization to indicate which of the two sets the pair come from. The reduce user-defined function uses the set identifier to disambiguate which pair comes first and which pair comes second. We presented the major ways to create map tasks and how to use them in the most typical cases. Manipulating multiple MapReduce objects enable to create complex applications. In particular, it is possible to recreate all relational algebra operations out of maps, reduces, and cross-products. There are more details in MapReduce MPI than can be covered in a couple of videos, and I encourage you to read the documentation if you have any doubt.